thank you all for coming. It's a real pleasure to be here. I've had a wonderful time so far. I had a chance to meet some really excellent people, and I'm looking forward to talking to more of you as time goes on. Also, I understand there's some people online watching this, and I want to greet you, even if I can't do that personally. But thank you for taking your time to be here. What I want to do is to talk about nitrogen cycling and availability and its controls. And in doing this, I know I'm talking about an area that Jack Brookshire has done an enormous amount of work in, and I hope he will be all right with me plowing shallowly over this area, in which he's plowed deeply. But this is, what you can do in an hour rough cut is plow fairly shallowly. And I'm really interested in nitrogen cycling and what controls the availability and supply of nitrogen, because it's something that people who work on ecosystems from a biological perspective find really fascinating, because at least outside of the tropics, it's the soil-derived resource that is most often constraining to plant production in natural ecosystems and in many managed ecosystems as well. So it receives a lot of focus from people with more biological orientations for that reason. For people who come at ecosystems from more geochemical orientations or soil-based orientations, it's not really such a central element, because, as I will suggest and try to develop here, it's not something that is a primary control over how things work. While it's often the proximate control over biological processes, it's not an independent control. And people with more soils or geochemical foci think of it as something that's part of the process, part of the package of controls, rather than a really strong independent control over systems. And to illustrate that, I will hope to advance the slides here. They advanced when I was trying this before. Maybe they'll work here. Nope. Well, there's bound to be a way. There it is. Okay. This is how I think about the controls of nitrogen in ecosystems and overall controls of ecosystems. There are a set of independent controls over the structure and functioning of ecosystems that include climate, parent material, relief, organisms, and time, the factors that Hans Jenny talked about many years ago. Late in his life, he recognized human activity was also one of these important and independent controls. These independent controls drive changes in ecosystems, controlling, in the long term, soil properties, rock-derived elements and soil properties, controlling biological communities, plant, animal, and microbial, controlling, importantly from our perspective, biological nitrogen fixers, the organisms that have the capacity to take nitrogen from its main Earth system reservoir, the nitrogen gas in the atmosphere, and convert it into biologically available form. And then finally, all of those together influence nitrogen pools, nitrogen availability, and nitrogen cycling. And the places where nitrogen is really an independent factor in the world are the places where people make it so. When we add fertilizer, that's an independent control. Where there's nitrogen deposition resulting from human activity, that's an independent control. But most of the time, it's a reflection of other controls. And my interest is, what are those other controls? And what's the pathway that takes us from ultimate controls through various levels of control to nitrogen pools, availability, and cycling? I want to get there because it is, in fact, the element that proximately controls many biological processes in many ecosystems of the world. Now, in thinking about this and talking about this, I'm going to take a fairly long-term perspective. I'm interested in the pool's availability and cycling. And because I'm taking a long-term perspective, I'm interested in where nitrogen comes from, how it enters ecosystems, and how it leaves them. not the sort of dynamics that occur when microbial populations take up and release nitrogen on a time step of seconds or minutes, but on the processes that take years, decades, centuries, and control nitrogen balance in whole ecosystems. I think the intellectual challenge behind this, behind dealing with an element that is not really an independent control and yet controls a lot, is reasonably summarized here. We know that an insufficient supply of reactive nitrogen constrains the productivity and many other aspects of many terrestrial and coastal marine ecosystems. Most such ecosystems contain organisms, or could contain organisms, with the ability to carry out biological nitrogen fixation. They can get nitrogen from the atmosphere, bring it into biologically available forms to support their own metabolism. So why don't organisms that can perform this biological process add enough nitrogen to ecosystems to, in the long term, reverse nitrogen limitation, or nearly so? It seems like since they're not constrained by nitrogen, they should add enough to where nitrogen's no longer a constraint, and they no longer have a competitive advantage. Now, there are answers to that, and part of the answers that people first jump to is nitrogen fixation is a costly process. It takes energy for organisms to fix nitrogen biologically. And so perhaps the constraint can be found in the cost of biological nitrogen fixation. But there's a cost to not having enough nitrogen too. And when non-nitrogen fixers have to acquire more nitrogen to, say, compete with biological nitrogen fixers, when nitrogen is in limiting supply, they have the cost of building more adsorptive area, getting better symbionts, producing enzymes and releasing them into the soil to break down lignin protein complexes. It's costly to get nitrogen in a nitrogen constrained environment. So a subtler way of saying the constraint or the paradox is biological nitrogen fixation, it seems like, should increase nitrogen supply to the point where the marginal cost of fixing a unit of nitrogen is equal to the marginal cost of acquiring a unit of nitrogen when it's in short supply. And so the way that it seems like the world should work is that nitrogen fixers would respond to and nearly reverse nitrogen deficiency up to that marginal cost trade-off in most of the world's ecosystems. And so nitrogen limitation to plant production and other ecosystem processes would be a transitory or a marginal phenomenon. In contrast, the way it does work is that especially in the temperate and boreal zone, nitrogen limitation is widespread. In agriculture, where it is not hard to explain, and in other managed and unmanaged ecosystems, where I think it's more difficult to explain. Nitrogen fixers don't respond to nitrogen deficiency with increased populations and activity in those areas in many ecosystems, notably late successional temperate and tropical forests. And the question I want to address is, why not? Why is nitrogen a resource in short supply, given what I think is some compelling logic that it shouldn't be? The world is telling us there's a lot we don't understand here, which we knew, but this is an important thing that's really pretty fundamental, that we don't understand about ecosystems. And I want to, as something as an aside, say nitrogen limitation in intensive agriculture is not difficult to explain. Harvest removes a lot of nitrogen from ecosystems. The remaining nitrogen is mobile and relatively readily lost from systems during non-cropping period. Nitrogen fixers that colonize agricultural systems during the cropping system are weeded out of cereal crop, and nitrogen fixers that occur in crop rotations mostly supply their own nitrogen, not a lot more. And so the removals and losses of nitrogen in intensive cropping systems have to be replaced. and replacing that nitrogen with fertilizer nitrogen transforms the global cycle of nitrogen. So we've really tremendously altered the global cycle of nitrogen because nitrogen limitation in agriculture occurs for reasons that we understand fairly well. But the scale of that change is a remarkable thing. I've done some calculations with colleagues of what biological nitrogen fixation was on land before humans so substantially altered the nitrogen cycle. We estimate that less than 50 million tons, it's a big unit, of nitrogen were fixed biologically every year on land. Now we fix 100 million tons of nitrogen for use as nitrogen fertilizer every year. We have other industrial uses. Agricultural biological nitrogen fixation is about as large as the whole of background biological nitrogen fixation. Fossil fuel fixes or mobilizes some more. In sum, we're producing and applying, or distributing at least, about 200 million tons of nitrogen every year, which is 4 or 5 times greater than the sum of all nitrogen fixed biologically before. And the world is transformed by that additional fixation of nitrogen. And how that additional fixation of nitrogen by human activity, just distributed in a very widespread way, interacts with the fact that many of the world's ecosystems are limited by nitrogen or constrained by nitrogen, for reasons I would argue we don't understand very well, is a really important global change whose implications depend very much on why nitrogen is limiting in the first place. That's just repeating what I said. Another important aspect of this change is that human health is substantially influenced by atherogenic nitrogen. There's an estimate published by the European Union's nitrogen assessment in 2011 that about 2.6 million years of human life are lost to excess reactive nitrogen per year in the European Union. The estimate for China is about 17.5 million years of human life are lost to excess nitrogen per year, mostly due to air pollution with small diameter particulate material, which contains a lot of reactive nitrogen. A lot of it's ammonium sulfate or ammonium nitrate aerosol. And this is obviously highly significant human cost. This actually turns out to be a very difficult number to get. I was surprised because it's really easy to get estimates of the economic losses of reactive nitrogen in the US and the European Union. Most of those as health costs, as years of life lost. But if you try to get that to a calculation of the actual number of years of life lost, well, the Europeans actually provided enough data so you could do that. The US assessment doesn't. It's all dollars. And so when you get into comparing different countries, you get into the very unfortunate thing of how much is a life worth in different cultures. I prefer to think in terms of millions of years of life lost rather than in dollars, yuan, or euros. So to understand the paradox of nitrogen cycling and limitation, it's not just a question of how is biological nitrogen fixation regulated within nitrogen fixers, downregulated when nitrogen is abundant, or upregulated when nitrogen is constraining, for which there is wonderful physiological work on biological nitrogen fixers. But the broader question is, what controls the distribution and abundance, as well as the activity of organisms capable of biological nitrogen fixation? It's an ecological question, not a physiological question, or it's an ecological question first, and then a physiological question. And we have some possible explanations for that we've worked with some in both observations and models. Organisms capable of biological nitrogen fixation could be absent or inactive because they're constrained by different resources or differentially constrained by common resources compared to organisms that don't carry out biological nitrogen fixation. Another is that the costs or benefits of biological nitrogen fixation could accrue to different groups of organisms. A third is biological interactions with other groups of organisms constrain the abundance of nitrogen fixers, even though nitrogen's in short supply in ecosystems. And there's evidence behind each of these that's interesting. In terms of the constrained by different resources, there's a strongly differential requirement for molybdenum and iron. Biological nitrogen fixers need more or need some compared to most other organisms. Limitation by molybdenum occurs, but appears to be rare. Another possibility is that the nitrogen-rich lifestyle of legumes in particular, which are the most abundant group of organisms that carry out biological nitrogen fixation, could basically mean that when you get into systems where nitrogen's in relatively short supply because decomposition and nutrient cycling are slow in the temperate and boreal system, the only way you can possibly have a nitrogen-rich style is by fixing all the time. And there are other reasons you can't do that. Another argument is that is actually a nutrient-rich lifestyle, and legumes in particular typically need more phosphorus than other plants that don't fix nitrogen. And so you can easily show experimentally in some cases that nitrogen limitation is phosphorus limitation in disguise, that the biological nitrogen fixers are limited by phosphorus supply, but the other species in the community are limited by nitrogen supply. So those all occur. So does the fact that you can get differential costs and benefits. This is an analysis of biological nitrogen fixation occurring in a little bit beyond that. Is that not working? Okay.
I'm not sure.
Okay, fine. I know people here can hear me, but I'm not sure if everybody can.
Yep, now we're good.
Okay, great. I want to look at another side of the equation and think about look at nitrogen losses from ecosystems. They matter because where biological nitrogen fixation is unconstrained, where it can respond to deficiencies in nitrogen and really fix actively and add a lot of nitrogen to ecosystems, that's capable of blowing away any limitation. Right? That's able to add enough nitrogen to make systems not limited by nitrogen. But in systems where nitrogen fixation is constrained, you're still getting nitrogen into the system through rainfall and atmospheric deposition. If you have losses of nitrogen from that system, then if you don't have losses of nitrogen from that system, the nitrogen will just keep accumulating to where even the slow turnover of a large pool will provide more than enough nitrogen in the system. So for nitrogen to constrain ecosystems, biological processes in ecosystems, you have to both constrain biological nitrogen fixation and you have to have losses of nitrogen that the system, for whatever reason, cannot control. And I want to look at those losses briefly here, because that's kind of the work I'm focusing on now. We can think of losses this is restating the fact that even small inputs will eventually increase the size of nitrogen pool, but at least conceptually, inputs and outputs and losses of nitrogen from ecosystems could occur by processes that biota could control or that they couldn't control. And if you think of inputs, biological nitrogen fixation is obviously one that can be controlled by biota. Inputs by nitrogen fixation are a biologically controlled input. In contrast, atmospheric deposition of nitrogen, nitrogen dissolved in rain, falls equally on ecosystems that have more than enough nitrogen and that don't have enough nitrogen. It's not controlled by the biota of the recipient ecosystem at all. Similarly, if we look at losses, we think of nitrate leaching as being something that the organisms can constrain. If organisms are limited by nitrogen, they'll get nitrate out of the soil solution and retain most of it in ecosystems. Maybe there'll be times of the year it'll be lost when they're not constrained, but if they're active, they'll be able to constrain nitrate losses. There are reasonable arguments that leaching of dissolved organic nitrogen, large molecular weight stuff that's not readily taken up by plants or symbionts, not amino acids, but large molecular weight dissolved organic nitrogen, is not controlled by biota, and losses occur more or less in proportion to leaching intensity and nitrogen pools rather than demand. Lars Hedin has done some very nice work with this, and Steve Perrock has some experimental work following through on that. And so we can think of both controllable and uncontrollable inputs and losses of nitrogen from ecosystems. So recently I've been working on nitrogen availability and cycling on a climate gradient in Hawaii, where I'm particularly interested in understanding the constraints that nitrogen brings to the functioning of ecosystems on these gradients. And the gradient where I'm working is a really cool one. It's a rainfall gradient on the north end of the island of Hawaii that runs from systems that receive 3,300 millimeters of rain a year. That's a lot, right? 3,300 millimeters It's 130 plus inches of rain a year, down to areas that receive about 280 millimeters, or 9, 10 inches of rain a year, a linear distance of 11 miles away. So it's a very striking rainfall gradient. And I've been interested for a long time. My colleague Oliver Chadwick, who Jeannie worked with us as well, has worked on the pedology, soil development and dynamics along that gradient. We kind of avoided nitrogen in this, partly because Oliver, being a soil scientist, wasn't that interested in nitrogen, and partly because we were interested in constraints to traditional Polynesian agriculture in this area. And nitrogen is so mobile that what we see now, we figured would have no impact on what constrained Polynesian agriculture 300 years ago. Unlike phosphorus, which is immobile enough that current phosphorus pools could tell us something about pools 300 years ago. So we decided, nitrogen is derivative. Nitrogen probably won't tell us much about traditional agriculture, but we know so much about the soils and climate in this system that it might be a really good system for understanding controls on nitrogen cycling. So we started working there with that in mind. This just illustrates some of the systems along the gradient, starting out in the upper left with systems that get over 3,000 millimeters a year, about 2,500, about 700, and about 250 millimeters. So it's a really striking gradient in a small area. And you can see we're in pasture along the whole way. And there are 2 C4 grass species that dominate everywhere. They trade off at about 1,200 millimeters. There's one in the wet sites and one in the dry, but they're in the same genus. So it's a pretty nice system for understanding things. And it's also nice in that if you think about all of the controls, independent controls I showed before, parent materials the same, potential vegetation is all reflective of the same things, topography is the same, climate is the independent factor that varies along this gradient. So we can sort of rethink our expected controls to run from climate rather than all the other factors to properties of soils, rock-derived nutrients and so forth, soil pH. Those in turn influence biological nitrogen fixers. Those in turn influence nitrogen availability and cycling. And all of these affect microbial community composition and functioning. Now, the current cool thing to do in ecosystem ecology is to analyze microbial communities and say that they're controlling the function of ecosystems. But they're at least as derivative as nitrogen is, right? They're controlled by all of the things that come above them in the hierarchy. It's rare that you could find a situation where you would say microbial community is the independent control. It's somewhere down the hierarchy. It's a really important control. It may be approximate control, but it's not independent. And we think that microbial community composition and function occupies about the same level of the hierarchy of controls as nitrogen availability and cycling. They control each other very importantly, but they're derivatives of things that happen at more ultimate levels of control. Okay, one of the things that's fun about this system, as I mentioned, is we know a lot about the soils and geochemistry. For example, we've used niobium. You don't get to say niobium very much if you're an ecosystem ecologist, but we've used niobium as a immobile index element in this system to index gains and losses of material into the soils. And what we see is if you start out dry, niobium concentrations decrease, because as you go from very dry to intermediate rainfall, you add organic matter and you add water of hydration to the system. And those both have the effect of decreasing the concentration of niobium. The amount of niobium doesn't change, but the concentration goes down. And then as you go into wetter and wetter sites, you leach away the calcium, magnesium, silica, and other more mobile elements and leave the niobium behind. And so niobium concentrations increase dramatically. And we have a really direct measure of the importance of organic matter and water of hydration additions versus leaching losses of mobile elements across the gradient. We've also looked at a number of other aspects of soils Oliver has over many years. I'm showing here just two of those measurements superimposed on the niobium. The red is the ratio of total aluminum to total iron. And as you can see, when you reach that threshold where leaching begins, you lose aluminum relative to iron. You go from a ratio of around 1 down to a ratio of about 0.4, very systematically with a striking threshold between them. For calcium, a highly mobile element, you don't lose much as you go from the wettest sites to mesic sites, but then you lose almost all of it. As you can see from total calcium, we're down to near 0 in the wetter sites, again with a striking threshold between the calcium abundant and the calcium depleted sites. And another set of things that vary in interesting ways, where we see that pH and base saturation is a bit like calcium. pH is more continuous, that the acidity increases with increasing rainfall across the whole gradient. pH gets lower and lower, which makes sense, of course. But a thing that doesn't vary linearly, or things that don't vary linearly at all across the gradient, are the biologically available calcium, shown here in red, this exchangeable calcium in the soil exchange complex, and resin extractable phosphorus. And those show a distinct peak at intermediate rainfall, with a very strikingly elevated availability of both phosphorus and calcium in intermediate sites. We know from a range of other work in these sites that what this reflects is biological uplift by the forest that was there before there was a pasture. The trees were rooted throughout the soil profile down to relatively deep places, especially in the drier environments. They pick up nutrients from deep in the soil, deposit it on the surface when their leaves fall. Phosphorus isn't very mobile, and so it all sticks in the surface soil. And this is a calculation based on the top 30 centimeters of the soil. When you get to wetter sites than that, the intensity of leaching is great enough to remove it anyway. When you get to drier sites, biological uplift isn't as important. The plants aren't nearly as productive. So there's this distinct pattern of some threshold variation in many of the nutrients, with a zone of really strikingly nutrient enriched systems in the middle part of the gradient. And we interpret this in terms of thinking about what we call pedogenic thresholds and soil process domains. Thresholds occur where there's a rapid or nonlinear change in soil properties in a brief interval along a continuous gradient, like you see when the calcium goes away, for example, or where the calcium, or total calcium goes away, or where the exchangeable calcium or resin phosphorus is enriched. In contrast, soil process domains represent the areas between thresholds where soil properties change relatively little across a wide range in forcing. And we use this framework to think about controls on nitrogen dynamics. We have domains where it's really dry and not very rich, but not poor, a domain where it's really rich in important plant-derived nutrients, and a domain where it's really acidic and really poor. And how does nitrogen cycling vary in those domains? We also, I'll go ahead one first before I go back. We also see that these, that middle nutrient-rich domain is a really important feature for human use of the environment. I showed this slide last night in my talk. This is a traditional Hawaiian agricultural system where Hawaiians intensified agriculture in that domain, in that nutrient-rich domain at intermediate rainfall, and sustained upland agriculture based primarily on sweet potato for a couple of centuries before European contact. See, can I go back is the question. Yes, okay. We also see that the microbial communities are vary as a function of these domains. The top figure here is the biologically available calcium and phosphorus. The bottom is the different domains we see along the gradient. And the middle is the second axis scores for an NMDS ordination of bacterial or archaeal versus fungal communities. If you look at the first axis of this multivariate characterization of communities, it correlates beautifully with pH and with the overall rainfall gradient. But the second axis sees what we see in the domain, sees soil fertility. And it's equally true for bacteria, archaea, and for fungi, just as it's true for humans. Human use of that area is really strikingly dominant. So what does nitrogen do? Well, this is what nitrogen does. The top shows the phosphorus and the calcium again. The bottom shows nitrogen mineralization, that is the release of nitrogen from decomposing organic matter, or nitrification, the production of nitrate. And it follows essentially exactly the same pattern as the phosphorus and calcium, with a peak at intermediate rainfall and really quite poor systems in much wetter sites, and moderately poor systems in much drier sites. The interesting thing about this is it can't be for the same reason. Nitrogen has a different source, comes from the atmosphere versus from the breakdown of rock, and its residence time in ecosystems is much, much shorter than that of phosphorus. It's the same pattern. Controls have to be related in some way, but they're not the same control. They can't be the same controls, and yet it is the same pattern. So we're interested in what's going on with this, what drives this. Now, this is something to really understand. We'll need to do some fairly long-term experiments. But what I think is going on is that in that middle domain, where nitrogen is really rich, there's lots of phosphorus and calcium. It's not too acidic. Great conditions for biological nitrogen fixation. And in fact, we see abundant biological nitrogen fixers mixed in here with the grass. This is a perennial soybean, Neotonia whitei, that was brought in as a forage. Can spread anywhere on the gradient, but where it is, and where clover is, and where other nitrogen fixers are, including indigo, is here in that zone where nitrogen is really rich. So it makes sense to us that biological nitrogen fixation is not constrained there, and it blows away any limitation. Nitrogen is really rich in that environment. If we think about the other domains, we think that middle domain, as I mentioned, high nitrogen fixation is what's important. But in the wet, infertile soils, we suspect that it's constrained in the long term by the fact that biological nitrogen fixation rates are low because phosphorus supply is really low. So legumes can't grow actively and can't blow away nitrogen limitation. Also, we think leaching losses of dissolved organic nitrogen in those high rainfall, organic rich systems keep nitrogen from accumulating and reversing nitrogen limitation in the long term. In the really dry domain, something that would be interesting to explore in these systems here as well, we think that it's driven by uncontrollable pulsed losses that occur when long dry soils are wetted up by rainfall. You know, that there's a brief period when the plants aren't active, but there can be lots of losses of nitrogen. And we think that the losses that occur then actually constrain the accumulation of nitrogen in the system as a whole in the long term. And that's sort of summarized in this figure, which shows in the infertile domain, we have lots of leaching, losses of dissolved organic nitrogen, some atmospheric deposition, but not much fixation. Here in that rich zone, we have lots of biological nitrogen fixation, balanced by leaching losses of nitrate, but with really rich nitrogen supply. In the really dry areas, we see pulse-driven losses, gaseous losses of nitrogen that occur when dry soils are wetted up. Like I said, really dealing with this will take, really understanding this will take longer term experiments, which are straightforward, but you have to have money for longer term experiments. Advantage of models is you don't need money. You can just model this stuff and it's cool. Trouble is you don't know if your model's right until you do the experiments, right? But we've done some experiments wetting up dry soils, and that's shown here. When we take the relatively dry end of the gradient, which I'm saying are fertile, mesic, infertile dry, and infertile really dry systems, I'm showing carbon dioxide losses in the solid lines and losses of nitrous oxide, nitrogen trace gas, in the dashed lines. And what we see is within 15 minutes after wetting up dry soils, there are enormous losses of nitrous oxide and more poorly quantified but enormous losses of nitric oxide, NO, and of ammonia as well. We see a pulse in respiration and carbon dioxide losses as well. But basically, once the microbial community really gets going and structured and organized after wet up, it constrains those losses. It's only in the first few minutes after things wet up that the losses are really massive from these systems. But if all of the activity is during these pulses, then you can have a system which is constrained from accumulating nitrogen by those pulse-driven losses that just occur occasionally. They say speculation until we can do the experiments, but reasonable speculation. The other aspect of this that's interesting is that we've looked at the natural abundance of the nitrogen-15 isotope, and this is an interesting thing to work on because losses of nitrogen from ecosystems that occur by gaseous pathways in particular, to a lesser extent nitrate leaching, but gaseous pathways especially, remove the light isotope from ecosystems and leave the heavy isotope behind, relatively speaking. They fractionate in favor of losing the light isotope and retaining the heavy isotope. And if you look at the nitrogen-15 abundance along our gradient here, you see that it's fairly constant in the infertile part of the environment, which suggests losses are not occurring by fractionating pathways. And then it goes up very steeply as you go drier and drier. This is a very typical pattern in ecosystems. Dryland systems are nitrogen-15 enriched. Wet systems are not nitrogen-15 enriched by comparison. I mean, you'll notice that there's what looks like it might be a little decline in the really, really, really dry areas. When I first did these measurements, I went, there's noise everywhere. That's nothing, right? Why pay attention? But then I read a paper from China that looked at a more than 2,000 kilometer gradient across North China, looking at mostly much drier systems than in the Hawaiian system. And they showed clearly that as you went from fairly dry to really dry, the nitrogen-15 abundance in the soil increased, same as in Hawaii. When you went from fairly dry to really, really dry, it became less fractionated. And when you plot those together, which I've done in the inset here, you see that if you look at the Hawaii data which are the solid points, and the Chinese data, which are the hollow points, they have exactly the same pattern. Something interesting is going on that involves the pathways of loss probably getting different again when you go from quite dry to really, really dry in ecosystems. And the Chinese had an explanation in their paper, of course, but it makes no sense whatsoever, sad to say. Unfortunately, my explanation isn't any better. So something we need to work with. But it's an interesting phenomenon because the advantage of experiments is you can see what's going on over a few years. The advantage of using isotopes is you're integrating over many, many years. And the two should complement each other. Actually, what I think is going on makes sense, but I have no evidence for it. What I think is going on is that in the really, really dry systems, when you get a pulse of rain, you lose nitrogen by abiotic pathways. But in the fairly dry systems, the losses are by biotic pathways. And so there's differential fractionation for abiotic versus biotic. It could be, but there's no evidence for it. That's a problem with that explanation. So, I've thrown out more than I've answered, but this is a rough cut, right? That's what you're supposed to do. And I'd be very happy to answer any questions and talk about any of this with any of you.
We have lots of questions. If you just push the closest microphone so our online people can hear as well.
I'm just curious how big these pulses that you're talking about are. Like, how much rain is that?
That's something that's poorly quantified. I have numbers for incubated soils that are pretty good. And you're losing in a single pulse by all of the gaseous pathways about 1% of the nitrogen in the soil. But that's in an incubation, in a mixed system. And so once we understand the processes and the important gases, that's an experiment we have to do in the field and compare the field versus incubation dynamic. Yes?
Your graph that was showing phosphorus and calcium versus mineralization and nitrification, there was a spike, another spike after like 3,000 millimeters.
Yes.
Do you have an explanation for that?
Yes, but it's equally unconstrained. So what I think is happening there is that the grazing intensity is less in the really, really wet environment. And so there's an opportunity for accumulation of nitrogen, some, in those wet environments. Not to a very high level at all. As you can see, it flattens out at a fairly low level. But in the between 2,000 and 3,000 millimeters, people are practicing, 2,000 and 2,500, people are practicing intense pulse-based grazing, which itself causes losses. And if you sample most of the time, you're seeing in a grading system that's accumulating nitrogen after that pulse. And so the availability is really low. And if you could integrate it over the grazing pulse, when the rancher won't let me on that plot, and the time between pulses, you'd probably see a smoother decline without a dip quite as low. That's my speculation. The rancher involved said I can go there this summer and see. So we'll see how that holds up. Because I love trying to think about different timescales of control and how they interact. And so that's a really interesting hypothesis for a timescale of control that's sort of on the months to years timescale, where mineralization, nitrification, immobilization of nitrogen are all sort of on the minutes to hours timescale, and inputs to outputs controls come on the years to millennia timescale. This is a nice intermediate one that would be fun to integrate into the analysis. Yeah.
So I'm thinking here about this calcium data and sort of long-term process and sweet spots. If we're thinking about that intermediate rainfall level, is that where we see
clay accumulation in soils such that we have more available, exchangeable calcium by virtue of that surface area, or is it simply exchangeable calcium normalized?
It's not normalized, but CEC does not have a peak there at all. In fact, if I were to plot CEC, it would go from about 40 milliequivalents per 100 grams in the driest sites, up to about 80 and then stay there all the way across. Part of that is organic matter in the wetter sites trading off for clay in the mesic site.
Right.
But it's not the CEC that is the dominant control here. It's the proportion of the exchange sites that are occupied by calcium. It's the dominant.
Well, and yet the development of that exchangeability might play a factor on the front end, right?
I think that the residence time of calcium on the exchange complex is so much shorter than the residence time for the development of the exchange complex. I don't think that's the important. Yeah, Chad.
What do you think about the relative shapes of the phosphorus versus nitrogen availability, the sharpness of the peak and the fatness of the tails? Is there a biological interpretation of that, or is that just noise?
Probably it's more than anything a trick of graphing. Right? I chose the scale. I made this is supposed to be you've seen this before, you're looking at it for reference, so I've kind of squished it. This is the new thing, so I've kind of expanded it. I think I think there's something real going on with the calcium never going way down, where the phosphorus goes pretty far down, the nitrogen goes way down in the dry sites. I think that's a real difference. But I think the height and steepness and sharpness of the peak is a cheap graph. Yes.
I'm curious about climate change and rainfall in your study, or what's the situation?
Well, the climate change is a really interesting question here. There has been some warming, but it's not very dramatic compared to the underlying gradient. There has also been some drying over the last 90 years. The challenge for me with agricultural restoration, which I'm trying to do in this area, has been that it got really, really dry between 2008 and 2013. And to the point where even on the wettest end of the traditional Hawaiian agricultural system, it was drier than the driest end had been before, when the rainfall maps were made. Now, that is a change in the direction that we expect from models of climate change in these systems. However, it's a larger magnitude of change than we expect by 2030. So it's kind of, do we know if this represents climate change or a fluctuation? No, we don't. It's in the direction of expected climate change. One of the interesting things with this, if I can go back a little bit, this is something that Jeannie and I have worked on also in both New Zealand and Hawaii, is if you look at the change that occurs here, in these systems, it's irreversible. The calcium is all gone away from these systems. So if it got drier, then it wouldn't be a matter of, you'd have systems that are now dry and really infertile. There's no way for a system to reflect, for the fertility of a system to reflect the new rainfall of the system. It's crossed a boundary, it's crossed a threshold. It's in an irreversible pit. And to the extent that's happening, climate change is a more profound change to ecosystems, because you can't just move things around as climate moves around. You've got a legacy of depletion of the soil that can't be reversed as the climate changes. That's what we think is going on in these systems. And we think if it does dry out, we'll have a new system, a novel system that is both dry and highly infertile, which doesn't exist now. Yeah.
I know you two have thought a little bit about in the New Zealand Hawaii comparison about the variability of the rainfall in your modeling and how that influences the patterns that you see across systems. Can you comment on that a little bit?
Sure. Yeah, the interesting thing is if you think of an environment as we were talking about earlier today as being the average climate all the time, then you develop a threshold like this, but it develops in a few thousand time steps and it never changes. But if you have year-to-year variability, then a string of 2 or 3 wet years pushes things farther into drier conditions. So if we look in Hawaii, going across the archipelago from this area, which is about 150,000-year-old substrate, to a 4 million-year-old substrate on the island of Kauai, the threshold has shifted way over to the left on Kauai, which wouldn't happen if you had average rainfall year after year. It's a shift that's driven by climate variability that runs the whole system. Yes?
Do you think the history of sweet potato cultivation in that little area has an influence on what you're seeing now in terms of the nutrient
Yeah,
values?
no doubt there's an influence of that history, but it doesn't create that area. We know that for certain. The reason we know it for certain is we can go to areas that are higher elevation and so too cold for sweet potato or other Hawaiian crops, and so which weren't farmed, but which have the same transition in water balance, and they're just as rich. We can also go within the field system and dig down through the field walls that they built and get the soil that was there before they intensified cultivation. I can't interpret anything from the nitrogen of that because everything's changed. But the phosphorus sticks pretty well. And that peak looks just the same as phosphorus. So the Hawaiians found and made use of a legacy of the pre-existing vegetation. They didn't create. Yeah.
I also wonder if there's any role for fire or anthropogenic burning of these fields that's showing up in your story.
We don't see it. We have some bogs that Sarah Hotchkiss has scored quite near this area. And well, there is certainly charcoal in the historic record. It seems to have more to do with European arrival in the area and the spread of pastures and grasses that burn readily than it does with the extensive Polynesian system that occupied the area. We know the Polynesian cultivators practiced shifting cultivation, slash and burn before they intensified production. But that seems to be an initial phase thing, and fire wasn't a big part of their sustained cultivation in these areas.
We have time for another question. I have.
Oh, yes.
So I'm thinking about that hump of nitrogen availability and phosphorus availability, and how in that far. Do you mind if we just look at it?
Not at all.
Just went away. If we look at that wettest zone, you had the combined control of possibly nitrogen fixers being phosphorus limited and nitrate leaching.
Yeah. Probably dissolved organic nitrogen.
Okay.
Not nitrate.
Not right. Okay.
We don't see much nitrate produced.
Okay.
I would have thought that denitrification could be a dominant control. We don't see much nitrate produced, and the little nitrate we do see produced, at least at the time that Karen Koskiati analyzed it for oxygen and nitrogen isotopes in nitrate, was N15 depleted compared to the bulk soil. It means it can't be denitrification. It's got to be partial nitrification.
You answered my question before. All right. Well, thank you. Let's give it a